Okay. So thank you everyone for joining us. Today we're going to start from the basics. So we're going to start from energy and electrical basics. I mean, this might many of us who I can see we have some electrical engineers and some other energy related engineers here, and this might sound too basic for you, but of course, why developing these modules, we had in mind that we may also have some participants who are not grounded in the field of energy or electrical basics, or who are not even an engineer. So we decided to start from the basic. I mean, so this is going to be about 8 weeks long training. So bear with us if you feel that this is too basic for you. But like I said, the purpose is just to create a background and then bring everybody at the same level of learning. And like I said earlier, more of the learning will also have to be on your own part as a participant. If you realize there are some certain areas of knowledge that I mean that you're not very comfortable with, it's now upon you to make the extra effort so they can be able to close the knowledge gap. So by the time we get to some certain level of complexity, you'll be able to follow us along through. So like I said, please bear with us if this sounds too basic to you. I don't think I need to go through this protocol. Ingenuity has already shared the profile of the trainers. And about the training, this training is to transfer knowledge and high-level understanding of energy and electrical basics. So the training is designed for engineers who would like to increase their practical competence and learn good practice methodologies. Now, like I said, we also have in mind that there are some people who are not engineers, like quantity surveyors, but people who are also in the engineering practice, or engineering related practice or energy practices. So it's not just strictly for engineers, but yeah, we know that engineers will have more like an advantage because most of what we're going to be talking about would have been part of what they learned in school. But we're also well aware that many of us have left the school environment for quite a long time, and we might be finding it difficult to deal with some of the energy or energy sustainability concept. So we are going to refresh our mind and memory about all of those issues. So the feedback of the participant will be considered, and like I said earlier, we are here to co-learn. So feel free to contribute where you feel that every other learners will share from your knowledge. So the training slide can be modified. So based on the feedback we got during this process, it is possible that we can modify the training model. However, it will be shared again after the training. So at the end of the training, participant will get the modified material. And like I said, let us make this interactive. So it's not just about me speaking. So let's also have some feedback. It also helps me understand that okay, I'm not alone in this. So let us first start with the concept of energy sustainability, because that has become the main thing. Everything about energy now is about sustainability. At the global level, at the local level, is about sustainability, and this is the reason. This is the driver of renewable energy. So, but just to unbox all of this concept, let us try to understand what we will say energy, sustainable energy or energy sustainability. What comes to your mind? I just want one or two persons to speak before I can proceed. I just want to know our different thoughts about what energy sustainability is. Maybe just one or two contributions. I mean, feel free to.
My name is Engineer Level.
Thank you, sir.
Yeah, I think energy sustainability has to do with meeting the energy needs of a particular business firm or industry. That's in simple terms.
Okay. Thank you for the contribution.
Hello.
Yeah, thank you.
Okay.
Go on.
Yeah, Chooks here. Well, for me, I see sustainable energy as energy that is delivered in a way that it has minimal impact, maybe whether economically or in other forms, just to in a way that reduces impact on the user, so it becomes a going concern into the future.
Okay.
That's
Okay.
my attempt.
Okay. Okay. Thank you very much. Yeah. So you both have spoken well. Engineer Dela, we talked about meeting the energy need of organization. Yes, meeting the energy need of organization is very important. But again, when you talk about energy sustainability, how do you meet the energy demand or energy need of an organization? Just like the Engineer Shooks also added to that explanation, how do you meet that energy need with less impact on the economy or on the environment? Because I mean, nature is sufficient on its own. Some people will say that nature does not need man; it is man that needs nature. So for the fact that with our energy comes from nature, how do we make sure that we harness that energy from nature with less destruction to nature? Okay, so that is the whole idea about energy sustainability. So the question on us as engineers or as energy practitioners is, how do we make sure that we're able to meet the energy demand of organizations or even as a country at large? How do we meet their energy need with less destruction on the environment? And that that has made a lot of, or that has created a lot of think tanks. Okay, and there have been so many methodologies, there have been so many practices on how to do that, but we all can all agree that we can only achieve this by two principles, which I'm going to talk about. Okay, and here are the two principles: energy efficiency and renewable energy. These are the two methods through which we can deliver sustainable energy. And I'm just going to through a little bit description about energy efficiency and renewable energy. So first of all, if you have an organization that needs, of course, they need to operate, they need to consume energy, okay? And you want to supply them energy that they can consume, and you want to meet that energy sustainability, the first thing that has to come to your mind is to, first of all, reduce waste. For every energy that you introduce or you produce, there's a consequence for every energy that you produce. So there is a CO2 emission that has to go with this energy that you produce, depending on the source. There is financial involvement for every energy that you produce. There are so many things that are involved in production of a single kilowatt hour of electricity or energy. There's so many things that are involved, and we're going to look at those things that are involved in that production of a single kilowatt hour of energy. Okay, so when I say kilowatt hour, just to say this ahead of time, when I say kilowatt hour, I know for most of us here, what comes to our mind is electrical energy. But as we progress with this training, you will now begin to understand that kilowatt hour is not just about electrical energy. There is kilowatt thermal, there is kilowatt mechanical, okay, and there is kilowatt electrical. So when I say kilowatt or kilowatt hour, don't just, don't be narrow-minded about electricity, okay? Energy exists in so many forms. We're going to go through all of that in the course of this training. So like I said, energy sustainability, the first thing that needs to be done is to first of all reduce losses. It does not make sense that an organization actual energy need, for example, is 100 kilowatt hour, okay? And then in that 100 kilowatt, okay, that's the actual energy need. But in the end, they end up spending like 150 kilowatt hour. What that means that 50 is being wasted. And you don't want to spend money at the expense of the environment producing 150 kilowatt hour, whereas what they actually need is 100 kilowatt hour. Maybe the excess 50 kilowatt hour is because somebody has left the fan or the air conditioning system or so many other things that have been left idle without doing any meaningful production. If this is an industrial facility, for an example, for commercial buildings, maybe somebody is not in a building or somebody is not in a space and the air conditioning is left working when there is nobody in that space. So all of these are losses that needs to be mitigated. Okay, so first of all, we need to eliminate the losses. When we are done with eliminating the losses, then the actual required energy, which is now the 100 kilowatt hour. Remember, this building or this company needs 100 kilowatt hour, but they end up consuming 150 because of the losses. Now you have to first of all identify those losses, and that's why energy auditing is important. when you conduct an energy audit, what you're actually looking for, you're hunting for losses. You're looking for those losses. That's why for any energy project that you need to do, the first thing that usually comes to mind is an energy audit or energy survey. Okay. Any energy project you need to do, you need to first of all conduct. It comes in different terminologies. Okay. Some people can call it feasibility study or energy feasibility study. It can be energy audit, it can be energy survey. Now it depends. Maybe by the time we talk about how to carry out energy survey or energy audit, you understand the different forms of energy audit. There are different levels of energy audit. There's level 1, level 2, level 3. So depending, but that's by the way. Let's remain on this track. So now you've ended up reducing the losses from maybe 150 to 100. That's the first point of call for energy sustainability, eliminating the losses. Now, this 100 that is actually needed, how can you produce this 100 kilowatt hour with less destruction to the environment? Okay. When we proceed with this score, you see how energy production, the traditional way of energy production is harmful to the environment, how it causes climate change and how it causes global warming and eventually a climate change. But I just want us to understand this concept and principle of energy sustainability. The first thing is to eliminate the losses or the wastages, and then the next point of call is to generate the required energy through a renewable energy source. Now, we're going to also see what a renewable energy source is, okay, and non-renewable energy sources. So if you generate it from a renewable energy source, now renewable energy sources cause less destruction to the environment. And that's why there has been so much, effort and financial funding going into renewable energy, because we have so much destroyed the environment that is now beginning to, haunt man by way of climate change. And that needs to stop. Otherwise, our future generation might not be able to survive on this planet Earth. So this is the entire concept of energy sustainability or sustainable energy. Now, what is energy in itself? I'm sure many of us, is not a new term for many of us. Energy, the word energy has its origin from Greek energia, which means activity, which means drive, which means vigor, force, power. All of this has common denominator, which is more like force. I mean, that is where we can define energy in different times. So it is the capacity to perform work or heating or cooling. Then energy is one of the most important concepts in natural science. Nevertheless, it is very difficult to define in few words. What are the needs for energy? We have a basic need for energy for preparing food. Now, everything we do, even as I speak to you, I'm expending energy. Everything we do, the device you're using to participate in this program, you're expending energy, you're consuming energy. For the fact that you're able to breathe, you're using energy. For everything we do has energy involvement. It has energy footprints. Okay, everything we do. If you take away energy from anything, then we become lifeless. So it's very, very important. So the basic need: preparing food, heating and cooling, personal hygiene, light, work, all of these are the basic needs. Now, for industrial processes, production, transportation, commodities, production of goods, all of this involves the use of energy. Now, energy exists in different forms, so many different forms. We have mechanical. These are primarily the forms in which energy exists. We have mechanical, we have thermal, we have electromagnetic, we have electrical, we have chemical, we have nuclear. So these are primary forms of energy, and they have other secondary forms of energy. I mean, so basically, what you're looking on your screen are the examples of these primary forms of energy, right? So electrical, you have power lines, you have lightning. Chemical, you have striking a match, and food, the food that people eat. Now, the food that we eat is a form of chemical energy. Okay, now the chemical energy goes into our body, and then transform into a kind of a mechanical energy by way of our movement through our muscles. So there are so many ways of energy transformation. We're going to go through all of that in the course of this training. Now, but let us come back to the source. Where does energy come from, and what is the basic law of energy, the law of energy conservation? So primarily, energy comes from the sun. Primarily, energy comes from the sun. So, but how does this energy from the sun, how does it begin to translate into mechanical, chemical, electrical, and so many forms of energy that we use, in our daily activity. So from the sun, it goes through the plant, through the process known as photosynthesis. We learned this in our basic science in primary school. Photosynthesis, a process where green plant converts, energy from the sun in the presence of oxygen into glucose. Okay, so these are the primary conversion of energy. And from there, both humans and animals will feed from this green plant. Then, of course, human beings also feed from animals except for those who are vegetarian, who doesn't eat maybe meat, but humans and animals feed from the green plants. And at the end of everyone's lifetime, whether humans, animals, or plants, everyone is retired and committed to the Mother Earth. Now it takes millions of years for this organic decays of humans or remains from humans, animals, and plants to convert to crude oil. Okay, it takes millions of years, not thousands of years, millions of years to convert to crude oil. Now, because of evolution of technology, industrialization, man needs a form of energy to power their economic activity. And somehow oil was discovered. There was a discovery of oil. Now, I want you to understand what has happened here. Energy comes from the sun. We use the energy to perform our activities on the surface of the earth, like feeding and other things. Then the energy is not sequestrated. Naturally, it is sequestrated. So it's more like it's been stored underneath the earth in the form of crude oil or other fossil fuel sources. Now, because of man's quest for economic development, man's quest for industrialization, we have found a way to explore this oil or the crude oil back to earth. So what we have essentially done is to introduce this energy back to earth. Okay, because we need this energy to power our economic activities. So when we bring it back to earth, we need to refine it into different forms, to serve the purpose that we need to use it. So it goes through refining processes. It comes out as petroleum. It comes out as diesel. It comes out as kerosene. And we use all of this to power our economic activities. We use all of this to power our economic activities. Now, in the end, remember that the primary source of energy is from the sun, which is heat, correct? Now, in the end of this, our economic activities, this energy goes back to heat, right? Now, when this heat is combined with the heat that is coming from the sun, it now causes excessive temperature rise on the earth of the surface. And this is what we call global warming, okay? And, when the temperature begins to rise, it begins to affect, so many ecological systems that makes it, difficult for man to survive on this earth. And this is what we call global climate change. Of course, global warming leads to climate change. And this is the problem that this is the world would I say the world largest problem at the moment, because everybody is trying to see how can actually prevent climate change, because it's affecting both developed and developing countries. It's affecting everybody. Now the funny thing is that even for those countries who has not significantly contributed to this crisis, in fact, most of them are the most affected. So Africa as a whole has contributed less than 5% to global warming and climate change, but we suffer the consequences as well, as much as those in America, as much as those in Europe. So it's like a shared, the global planet or the Earth is a shared platform for everyone. However, the activities of other people are also affecting affecting the lives of people who are in the far locations of other places. So this is the source of energy and how energy is being transformed into different forms that we use today. So then there's the basic law of energy conservation, which means that energy does not remain in the same form always. Now, to cause change, energy itself changes from one form to another. During changes, energy is always conserved. Now, this is just this is too much of terminologies. But the point here is that energy can neither be created nor destroyed. You cannot create energy, you cannot destroy energy, but energy can be transformed from one form to another. So in that process, energy is conserved. You cannot destroy energy. You cannot create energy. it primarily comes from the sun. So when you use energy, you're only using that energy as a process of conversion. So when energy is changing from electrical to mechanical or from mechanical to electrical, the process of that conversion, you exploit the transformation process to achieve what you need to achieve. But in the end, energy is conserved, and most times it goes back to heat. So I give you an example. When you convert electrical energy to mechanical energy, it causes motor to spin. That electric motor, it causes it to spin. Now, what's happening in that process? That electrical energy is being converted to mechanical energy, and in the process of that conversion, you create a mechanical movement around a motor system, and you use that motor system to carry out whatever activity that you need to carry out. But in that process, energy is not destroyed. Energy is only transformed. So this is basic law of energy conservation. If anyone has a question, please, you can just raise your hand and I will allow you to speak. So now there's another concept of energy and power, because a lot of times we use this word interchangeably, just to clarify that these are two different things. Energy and power are not the same. However, they are related, but they're not the same. I have even heard professionals, when they want to refer to energy, they say power, or when they want to refer to power. So it's used interchange, but it's good that we understand how these are different. Energy is the capacity to do work, which is force times distance. Okay. Now, these are fundamental definitions of energy. But again, it's different from power. Power is energy over time. Remember, energy is the capacity to do work. So you have the capacity to do work. That you have energy does not mean that you're using it or you have used it. Okay. When you start using that energy, then it's over time, it's power, right? So we are going to understand this by their by their units. Okay, so energy is kilowatt hour, whereas power is kilowatt. There is no time component in power. Just we have that basic understanding. So here is what I mean. Power is either watt or kilowatt. There is no time component. But energy has time component. So energy is power times time. So we refer to energy as kilowatt hour. So when you receive your energy bill or your bill from your distribution companies, what you will see is kilowatt hour. Okay, it has a time component, and power has no time component. Power is momentarily, okay, but energy is over time. Please keep in mind these two basic units, kilowatt and kilowatt hour. It's very, very important. There are different expressions of energy. So anytime I mention energy, please, I'm referring to kilowatt hour. Okay. So some people might also refer to energy as kilojoule, especially for those in chemical engineering or other forms of heat, especially when you're talking about heat transfer. In most times you can hear something like kilojoule or megajoule. They all mean energy. So, however, there's a connection of converting them from kilojoule to kilowatt hour or megajoule to kilowatt hour, and these are the factors of conversion. So for kilojoule, it is 3,600. If you multiply 1 kilowatt hour is equals to 3,600 kilojoule, and 3,600 kilojoule is equals to 3.6 megajoule, and then 3.6 megajoule is equal to 0.0036 gigajoule, so that we can all understand that it's not just kilowatt hour. Energy can also be expressed in other units, but let's just have this basic understanding of the energy conversion. And it's very important to be able to move energy from one unit to another. And like I already said, power is about watts, and watt is equal to voltage times current. We're going to come to this, but this is just a high level introduction about the program. So let us just do a little bit of exercise regarding energy and cost. Okay, and it also helps us to understand power and energy. So, what is the cost of 5 kilowatts continuous operation in a year? So, assuming that assuming that this is a motor, and when I talk about motor, I'm talking about industrial motor or the motor that drives equipment. So, what is the cost of 5 kilowatts continuous operation in a year? Now, in a year is 365 days. And this is a continuous operation for 24 hours. So that means that in a year, you have 8,760 hours per year. And the cost of electricity is 0.1 USD. Please ignore the USD, assuming that, of course, it cannot be naira anyway, but let's just ignore that value US, because of course we are in Nigeria and we ought to be using our local currency. But for the purpose of this example, just ignore that. So can we just quickly run a brief calculation to estimate the cost of energy? It might be useful to have a calculator, handy. Otherwise you can use your phone. But this is just a simple calculation. But for me, it's just for me to understand that yes, that we are following this, this basic understanding of energy and power. If anyone has done the calculation, you can post your answer in the chat group, or you can unmute your mic and just speak.
It's 4,380.
380 watts.
Let me say naira.
Yeah, okay. Or dollar, because we're actually using dollar.
Or dollar, yeah.
Okay. Any other person?
That is the answer.
Okay. So it's just a simple calculation. Of course, 5 kilowatt is power. But when you then multiply it by time, you have your energy, and energy is what you're actually paying for. You're not paying for power. But in some countries, you also pay for power. We call it demand. What again? Demand. Is it demand factor or what? I mean, no, not demand factor. I'm trying to remember exactly what you call it, but you pay for your demand. The level of power that you need, you pay for it. But we'll get to that. We'll talk about maybe electricity tariff. We can talk about that. But this is essentially the simple calculation that goes around this. Okay, sorry, I was thinking about demand charge. For some certain country, you need to pay demand charge. And demand charge is exactly how much power you want to contract from the utility. If you're in Nigeria, we really don't have that at the moment. But I think we are moving to a point where we need to have demand charge. It's basically applicable for industries, so you don't own your equipment, anyhow you want to use it. It's actually a way of, it's a way of implementing demand side management in the utility sector. But for now, let us remain with this. It's power times time, which is 43,800 kilowatt hour per year. Then a unit of that is 0.1 USD. And when you do that multiplication, you have 4,380 USD. That is the cost of energy for continuous use of this equipment for 1 year. Now, let's talk about renewable energy sources. When in my introduction, I talked about renewable energy sources and, of course, non-renewable energy sources, and the need to move from non-renewable energy sources to renewable energy source. The illustration I gave initially about the energy conversion from the sun, to human, to crude oil and back to earth, those are non-renewable energy source. But of course, in the midst of that, there's a renewable energy, because the sun itself is a renewable energy. Only that at the time, man does not have that knowledge how to harness the energy directly from the sun. But through science, innovation, technology, things has evolved and we now have, technology to harness the energy directly from the sun. And that's why we keep talking about solar panels today. Solar panel has become the main thing today, we'll talk about renewable. In fact, we'll talk about renewable energy. The only thing that comes to the mind of most people is solar system. However, there are so many other forms of renewable energy system. So solar radiation is a form of renewable energy. Hydro is a form of renewable energy. Wind, ocean-related energy, wave, tidal, thermal gradients, salinity gradient, biomass, food, like food waste from plants, instead of allowing them to decay and going underneath the earth, transforming, you can use them directly, and then if the process can still continue, they can still go down and then become fossil fuel. But while they are on the surface of the earth, you can use them, and they are considered as a form of renewable energy. You have biogas, you have geothermal. So we also have the non-renewable energy of which I explained earlier. The fossil fuel, you talk about the coal, the oil, the gas, and the nuclear energy, uranium. These are all forms of non-renewable. And the point that these energy sources, they can be depleted. I mean, what that means, you can actually use them up and you have them no more to continue using. And that's why they are non-renewable. But for every other form that is renewable, you can actually keep using them without, having to exhaust their sources. So let us now look at energy transfer base. Now, I want to assume that we understand the basic of energy in terms of definition and different forms in which energy exists. But now let's talk about energy transfer. How do you transfer energy from point A to point B? How do you do that? How does it happen? It happens primarily by three ways. You have mechanical transfer, you have electrical transfer, you have chemical transfer. So mechanical transfer is the movement of mass. For those of us who are electrical engineer, you can easily understand this. Any movement of mass is a mechanical transfer of energy. When you move from your sitting room to your kitchen, what you've used mechanical energy by that your movement. When you drive your vehicle from point A to point B, what you have done is a mechanical movement of energy. You have moved energy from one point to another through a mechanical means. There is an electrical means of energy movement, which is movement of electrons. So the wires that you see around the street, the high tension wires you see on the way, these are used for electrical movement of energy. And maybe by convention, electrical energy has become the most desirable form of energy. And this is because you can convert electrical energy to any other forms of energy easily, and that has made it, a more desirable form of energy. But just have in mind that one of the way of energy transfer is through electrical means, through wires. Okay, and when electron move through these wires, you actually transfer energy from one point to another, and that is the way through which the electricity that we consume in our various homes comes from. Because this electricity are generated in faraway locations, and they have to move through those cables to get into our home, and by way of movement of electrons. Then we have chemical means of energy transfer, which is the movement of atom by conduction, by convection, and by radiation. We're also going to look more into this form of energy transfer, because when you go to industries, if you want to conduct an energy audit for an industry, you most likely going to see a lot of this chemical movement of energy, through heating and cooling. When you're doing heating and cooling, essentially what you're doing is movement of atoms. Okay, and most things that happens in the industry, you have these basic three forms of energy movement in industries. When your electric motors are moving, their mechanical energy movement. Of course, the electricity has to be introduced into those mechanical devices to convert into mechanical energy. When you're doing your process industries, you're heating, you're cooling, all of this are chemical movement of energy. So we'll get into all of these details. Okay, so like I said, I want to also dive in a little bit more into chemical form of energy transfer, which is movement of atom. And by movement of atoms, this can happen in three forms or three methods: by heat conduction, convection, and radiation. So by heat conduction, we mean the heat transfer by molecular contact. So when the easiest way and the most basic way for me to describe this is when you're cooking or when you're boiling water in a kettle. Now, when you lit the gas, the energy from the gas is actually a chemical form of energy, but it then transforms into a heat form of energy, which is still a chemical form of energy. But that energy is transferred from that gas or from the fire to your kettle through a means of conduction, because the fire is actually touching the kettle, and then the heat is then transferred from that fire to the kettle. So it's a process of energy transfer through conduction. They will have energy transfer by convection. Now, this is heat transfer through density difference, most effectively in liquid and gases. Now, I still go back to the process of heating water or boiling water in a kettle. Now, when you move energy from gas to heat, which is the fire, to the kettle, now the water inside the kettle absorbs this energy from the metal part of the kettle, and the water that is at the bottom of the kettle absorbs this energy first, and it gets heated. It increases in temperature. But of course, how does this heat move to the water that is at the top of the kettle? Now, the process of this movement of heat is known as convection, which is the transfer of heat through density difference. Because when the water at the bottom of the kettle absorbs the heat, it creates a density. It becomes lighter. Okay, so once they becomes lighter, they move upwards, whereas the water that is at the top of the kettle, which is cold, they are denser. The density of that water is heavier. They will move down, and by that movement, the heat is transferred from the bottom of the kettle to the top of the kettle, and by so doing, you have an even distribution of heat. At a point, the water will begin to boil. Okay, so this is the way that through which energy is moved through liquid and fluid or gases. They will have thermal radiations. Thermal radiation is a way, it's a heat transfer by wave motion. This is the way through which radiation from the sun reaches the earth. So no material is required. It can occur in space. So these are the three forms of heat transfer. And most essentially, these are applicable in industrial processes, but in our basic life, we can also see how these are also applicable. So there are two types of heat. I want to crave most of what we're going to be talking about might have a little deviation from what many of us might have thought about maybe energy, which is electrical. We are going to, in the course of this training, we are going to, expose us to different forms of energy and how they are used. Electrical is just one aspect of. In fact, when it comes to industrial processes, electrical is not the most used energy in industry. In most cases, thermal energy are the most used energy for some industries, but we'll get to have that on, and that's why we'll keep talking about heat or cooling or heating. Okay, I just want you to understand the reason why we're talking about this, because when you go to an industry, you're not going to be seeing so much of electrical or electricity. You're also be seeing a lot of mechanical and chemical forms of energy. You're going to be dealing with boilers. Okay, now this training is not focused on solar system, because I know some of us came to this training with that mindset that, okay, I want to also, broaden my knowledge about solar systems. Yes, we're going to come to that in the later part of the training. But if you remember in my introduction, I had mentioned that for sustainable energy to be effective, you have to first of all manage the losses. And what we're doing now is a process of making you to understand how to manage those losses. If you're able to manage those losses, then you cannot talk about renewable energy, which is the solar system that some of us are very comfortable with. But please, just bear with us while we go through this other processes of energy in industrial applications. So we have sensible heat and we have latent heat. Now, sensible heat is what many of us can relate with, which is the energy, the heat that we can sense. When you touch a kettle that is boiling, that is the sensible heat. You can sense it, of course. That's why it's called sensible heat. But there's another form of energy, which is latent heat. When you boil water up to 100 degrees centigrade, you get to the boiling point of that water. Any heat you keep adding to that water, and heat is also a form of energy. So any energy you keep adding to that water will not increase the temperature. Rather, what is going to happen is to use that energy to change the phase. It will change from liquid to gas. So that's at that point when energy is being converted from one state to another state, it's called latent heat. So energy that is needed to change a substance from one form to another. So change water in liquid to form vapor is a form of latent heat. So I hope we understand these two different things. So when we are cooling our facilities, your air conditioning system actually uses sensible heat, but there is also a latent heat component of your air conditioning system. So for example, the humidification of the air in your space. When you're using an air conditioning system, you notice that there is water dripping outside from the condenser side. So that form of energy that is used to convert the vapor back to liquid is a latent heat. So this is just a typical illustration of how sensible and latent heat operates. So when you have an ice and you keep applying heat to that ice, it will get to a point where the ice begins to melt. At that point, when the ice begins to melt, any heat that you keep adding to that ice will not raise the temperature. Rather, it will use that energy to convert from solid to liquid. That's when the ice will melt. And after the ice has melted, you keep adding the heat. The temperature will then keep rising until it gets to 100. Once the temperature gets to 100, it gets to a boiling point. At that point, every heat you're adding to that liquid will not increase the temperature beyond the boiling point, which is 100. Rather, the heat will be used to convert from liquid to vapor or gas or steam. In the case of water, it will be converted to steam. So that is what actually happened here until the water has been converted to steam. And if you keep adding heat to that steam, you have something that is called superheated steam, which is a high, concentration of energy. So let's look at utilization of energy. Now, to understand the utilization of energy, I want us to understand the coefficients of efficiency. Coefficients of efficiency. Efficiency is very, very important in any process. In the energy system, efficiency is very, very important. Because without efficiency, you might not be able to understand losses. You might not be able to, manage losses. But let us look at it from the power generation point of view. The energy or the electricity that we use in our various homes and offices, where does it come from? What are the losses that happens before this electricity gets into our home? Okay, so now let's look at it from this way. You have 100 units of energy from the generation point. So, for example, if this power is generated in Egwin, for example, or Azura Power in Edo State, or some other location where this power is being produced, you have 100 units of energy contained in the fuel, in the gas that is fed into the power plant. You have 100 units of energy. By the time that energy is coming out from that power plant, you will have lost about 70% of it. So of the 100 units of energy that's contained in the fuel, 70% of it has been lost through heat losses, through mechanical. You remember the sound, or the sound that are coming out from those power plants. Those are energy losses. You remember the heat radiations when you move around those power plants. Those are losses. So all of this is what accounts for these 70% losses in those power plants. And when you move those electrons, like electrical energy, through the cables, you also have resistance, you also have losses, which is about 9%. In the Nigerian system, I think the regulation actually, put these losses about 8%, if I'm not mistaken, about 8 or 7%. The transmission losses is about 8 or 7%, but for this illustration purposes, it's about 9% losses when you move this energy from the generation point through the transmission cables. Okay. Now, this is 9% is even transmission and distribution. In the Nigerian case, I think 7% for transmission and 8% for distribution. I'm not so sure, but in that, something close to those values. Okay. Now, these are the losses that occur through the transmission and distribution. And then it gets into your facility. Then you have your equipment. So, for example, this is a motor that drives a pump. So, for this motor, there are also losses in the motor. When your motor is working, there are sounds that you hear. The motor is also being heated, just like generator. These are energy losses. So you may lose about 10%. from this point, and then you keep, now the motor drives a pump. Motor and pump are not the same thing. Motor drives a pump. Okay. So when the motor drives a pump, there could be also losses in the pump, okay, which in some cases could be as much as 25%. Now, there's a way to optimize the use of a pump, which could include the use of variable speed drives, on these motors and some other things. So we're going to talk about that when we get to energy efficiencies in pump. But you have about 25%, okay? In some cases, you might have valves to throttle or to reduce the pressure. But the long and short that of the 100 units of energy that you started with, in most cases, you end up with less than 10% or 10 units of that energy. So you can now see that about 90% of the energy that you started with are lost along the process of generation and transmission and distribution. And for every unit of energy that you use or that you waste, about 90% or 9 units of those energy are wasted just to produce 1 unit of energy. So you can begin to appreciate the importance of energy conservation. So when you say 1 unit of energy, you're not just saving 1 unit of energy, you're also saving all the losses that accompany the production of that 1 unit of energy. And all of these losses are what actually is going to included in your bill. Because for somebody who is producing this, transmitting this, and distributing this energy, they have to recover their costs. So all these losses are included in what you pay in your electricity bill. Okay. In the design of the electricity bill in Nigeria, some of these losses are included in the tariff design to recover these losses. So this kind of trying to explain the importance of energy efficiency in every system. You can save a lot of money for industry through, practical implementation of energy efficiency. So this is essentially the formula of efficiency: useful energy over energy. So if you look at the situation that I have just illustrated now, the useful energy is 9.5 units. Now the energy that we started with is 100 units. So you can see that the energy efficiency in this case is 9/100, which is about 9% of the 100 units of energy that we started with. So it's very, very essential that we understand this concept. Now let's also look at energy indicators. What's the meaning of energy indicator? Energy indicator is something that tells us how efficient a system is, or how efficient an economy is in managing the energy, for their GDP production or for their GDP, right? So it's something that tells. So if you look at industry and we say that this industry is more efficient, or industry A is more efficient than industry B, what are the basis of comparison? How do we know that, okay, industry A is more efficient than industry B? Okay, so how do we do those comparisons? How do we do benchmarking? If you want to benchmark your energy use to your competitor, how do you do that? And that is what energy indicator helps us to do. So there's what we call specific energy consumption. And this is the ratio of energy consumption to the corresponding production quantity. So for example, if Dangote is producing 1 bag of cement and Dangote is using 10 kilowatt hour of energy to produce 1 bag of cement, and for example, BUA is using 15 kilowatt hour to produce the same bag of cement, who do you think will sell cheaper in the market? Now, this is a question. Dangote is using 10 kilowatt hour to produce 1 bag of cement, and BUA is using 15 kilowatt hour to produce 1 bag of cement. Who has a better competitive advantage?
Dangote, of course.
Okay, so clearly Dangote has a better competitive advantage. Now, this 10 kilowatt hour per bag of cement and 15 kilowatt hour per bag of cement is what we call specific energy consumption. It's an energy indicator. It tells us who is consuming more energy. Okay, now this is about industry. So we can also talk about this energy indicator for economic scale, economic wide scale for a country. So for example, Nigeria, we can say for every GDP that Nigeria generates, Nigeria consumes, for example, 100 kilowatt hour for GDP. Now, GDP is a lot of activity, so it's not specific. There's a lot of activity that goes into it, and that's why it's called energy intensity and not specific energy consumption. Okay, so this is this is at a higher level to compare energy consumption of maybe countries. So that's what we call energy intensity. And at the global level, maybe at the UN level, they use this terminology to see which economy is more efficient than the other. And based on the existing data, I think based on some study that GSA has done in Nigeria, there are reports that Nigeria consumes 40% more energy per GDP compared to other countries like Bangladesh, Indonesia. I mean, some other country that at a time we are at the same developmental level with them. Bangladesh, India, and some other country. Nigeria consumes 40% more energy per GDP. So that actually tells you there's a lot of opportunity to implement energy efficiency in Nigeria. And it's actually clear because for production in Nigeria, for manufacturing in Nigeria, you find out that they are not competitive. You spend, apart from other factors, because it's not just about energy, there are other cost elements that actually makes them not competitive when you manufacture this in other places in the world. I know there are tax, companies, there are also maybe like the multiple taxation and so many other things that are involved. But again, energy also has its own component because most of them has actually cried out that the cost of energy is killing their business, right? And reports also has that Nigeria consumes 40% more energy, per GDP than other per country. So some of these industries are actually using 40% more energy than other countries. So there is clearly opportunity for energy efficiency or energy management or energy reduction in these industries for them to be competitive. So this is just to help us understand how you can actually compare or benchmark energy consumption either between industry or between economy. So that's what energy indicator helps us to understand. Now let us go to the electrical basics. So, or electrical energy. So now, what are the basic electricity? Okay, when we talk about electricity, we often talk about voltage, we talk about current. These are the two primary elements of electricity. Now, voltage is what pushes electricity through a circuit, which is the driving force. For some of us who are electrical engineers, this is nothing new to you. But some of us who are not electrical engineers, yes, we can understand electricity, but we may not have appreciated electricity in this way and manner that I'm trying to illustrate electricity. Okay, and the best way to do this is to use an analogy of a water. Okay, now a lot of time you hear people say that there's low current. Okay, there's nothing like low current. What actually happens is low voltage. As professionals, we should also understand what is happening when your light bulbs are not being are not working properly when they are low, instead of working at a certain voltage. So it's not actually a low current, it's actually a low voltage. So let me use water analogy to explain this. What you actually consume is current. You don't consume voltage. What you consume is current. So it's like water. What you consume is water and not the pressure that is pushing the water. So the pressure that is pushing the water is voltage. But what you actually consume is water, right? So the same way it works in electricity. What you consume, what your meter reads is current. What you're paying for is current. But that current should work at a certain voltage, and that's why we have regulated voltages in Nigeria at different levels. For the domestic consumption, at our voltage is 230 volts. 230 volts. That's the standardized voltage through which your electricity should be supplied from your utility. So when it goes below some certain degree or some certain percentage, it begins to violate the regulation, because ordinarily those currents should come at 230 volts, plus or minus some percentages. Okay. So volt is what pushes the electricity through the circuit, which is the driving force. Now, current is measured in amps, and this is what is pushed through the voltage, or what is pushed by the voltage, and it is the flow. So electrical power is when voltage and current work together to do something useful, such as turn a motor or light a lamp. That is electrical power. Now, what is a measure of power or electrical power? And then what is voltage times current? or volt times amp. Amp is current, volt is voltage, okay? Then times power factor. We are going to talk about power factor, in the course of this training. I think for this session, we're going to talk about, I'm going to be a little bit more faster because, our time is fast spent. Now, there are different forms of electricity, or different types of power, actually. There's apparent power, there's real power, and there's what's the other one again? There's apparent, there's real power, and
Active power.
yeah, thank you. And there's active power. So there are different types of power, actually. So we are going to get to that. Sometimes this escapes my mind. There are different types of power, and we're going to get to that in the course of this. But the reason I'm saying this is because you also see VA here. Okay, this is voltage ampere, which is volt times ampere without power factor. So this is a different form of power. Okay. Now, what is an active power? Now, this is an apparent power. The VA is an apparent power, and this is an active power. The watt is an active power. We're going to get to that in this training. But before we do that, let us understand different phases of electrical system. There are different phases of electrical system. There is single phase and there is three phase. Now, the single phase, this is the power system having only one sine wave, and the frequency of that sine wave is 50 hertz. Or 60. In Nigerian case, our frequency is 50 hertz. In some other places, I think in US, I think it's 60 hertz. Now, this is country dependent, right? It depends on the country, and the hertz is more like, it's just the frequency of the wave, like I said. So for a single phase, this is a system that's just having one sine wave. I know for many of us in our homes, you see 4 wires. That you have 4 wires coming into your facility does not mean that your facility is 3 phase. It doesn't mean that. Out of those 4 wires, only one phase will either be connected, except your building has large equipment or is an industrial facility. That's only when you can have maybe those 3 wires or 4 wires connecting into your facility. But as long as is a residential building, I don't have high energy equipment in the building, most likely what you have is a single phase, just one neutral and one light. That's what you get connected into your facility. So it's a single phase. Then we have 3 phase. 3 phase, this is the power system having 3 sine waves, and the frequency of each of the sine waves is 50 or 60, depending on the country. Now, the 3 sine waves are separated in time with a phase angle of 120. A phase angle of 120 between the sine waves. So we have the red, yellow, and the blue phase. Now, this is most applicable in industrial processes. For most of these industrial machines, you actually have all of these phases connected to the machine. Both the red, blue, and the yellow phase connected to one machine. And of course, depending on the type of connection, you could have delta or star, but that's by the way. Now, this is the different types of connections to equipment. In some cases, you could have the 3 wires connected. In some cases, you have 4 wires connected to this equipment. So these are 3-phase system. Now, when we talk about the phases of electrical connection of electrical system, we have single phase and have 3 phase. It's also important we talk about power quality, the quality of electricity that is actually being connected to all of this equipment, and how they also affect the functionality of this equipment. So power quality is related to how well an electrical system maintains a pure sinusoidal waveform at rated voltage and frequency. I want you to note this 2 words, voltage and frequency. We're going to talk about them, how they affect the quality of power system. So power quality issue involve all momentary phenomena, including spikes and outages, as well as harmonics. You're going to talk about harmonics. Modern electronic equipment both causes and is affected by these problems. So power quality is becoming one of the most important issues in energy management today. Remember, the purpose of all of this is for participants to be able to effectively manage energy in wherever they find themselves. Whether in your home, after this course, you might begin to discover some energy losses in your home, and you begin to take measures to actually correct them and improve them, or to eliminate these losses, before you can begin to talk about how you now provide this energy with renewable energy sources. And one thing I also didn't mention is that once you're able to eliminate energy losses in a particular facility, you also reduce the cost of implementing renewable energy. Because you can imagine if you want to implement a renewable energy for a facility that is consuming 150 kilowatt hour, you're actually going to spend more money. But if you're able to reduce that to 100 kilowatt hour, then that means you're also going to size your equipment lower, which is actually going to reduce the cost of implementing renewable energy systems. So the benefit and importance of energy audit and energy efficiency is actually enormous, you know. So let's start with harmonics. So harmonics are a distortion of normal electrical current waveform, generally transmitted by a nonlinear load. Remember, we talk about power quality. There are some certain, parameters we use to, determine the quality of a power system. One of them is harmonics. So these are distortions to normal electrical current waveform. Remember when I talked about single phase and three phase, I said these are electrical waveforms. Okay. So once these waves are being distorted from the normal form they are formed, then you begin to have things that we call harmonics. I will explain that further in this presentation. So in other words, harmonics are multiple of fundamental frequency. Let me just use this diagram to illustrate it. So this is a normal waveform of an electrical system. Now, this is a single phase system. Now, this is a normal waveform of the electrical system. But there could be unhealthy waveform of this electrical system. Now, this is what you could have. Instead of completing, one waveform, before it actually completed, you now have a multiple, wave. So the red, now I want to look at the fundamental frequency here, which is the red. The red wave is the fundamental wave frequency. This is red one. Okay. Now when this system is affected by harmonics, you can see this other light red color wave. So before it actually completes one wave, you can see that you have like three, 1, 2, 3, before it completes one. And this is what we call harmonic. So it affects the fundamental fundamental current, which is the red one. And once that is being affected, what you're going to have is the blue one, which is the third harmonic. So before it completes one, you have had 1, 2, 3. So this is what we call harmonics, or harmonic distortion in an electrical system. So this is how it happens. This is the normal, undistorted, and fundamental frequency. Once there's a harmonics distortion, this is what you end up having. So this is an unhealthy current. Okay. So once you have this kind of system, this kind of thing, it affects the quality of the power. It affects the functionality of machines, especially for industrial systems. This is a very big problem for industrial systems. So what are the causes of these harmonics? Harmonics are generated by solid-state-based equipment, such as switching power supplies in PCs, DC drives, variable frequency. So any system that converts AC current to DC current introduces harmonics. So those are non-linear loads. Okay. Remember what we said here that where is that point? Okay, like I said, harmonics are generally harmonics are the distortion of a normal electrical current waveform, generally transmitted by a non-linear load. So what are these non-linear loads? These are examples of those non-linear loads. The switching power supplies, variable frequency drive, and like I said, generally, any system that converts AC current to DC current is a non-linear load. So most power systems can accommodate a certain level of harmonic, but we experience problem when harmony becomes a significant component of the overall load. Now, I don't know if some of us have had maybe an experience or had this mentioned somewhere that an LED lighting introduces harmonics into the electrical system, and that's because LED lights are electronic equipment. They are different from the resistive filament that we have in the past, which is the yellow light that we use, the incandescent light bulbs. Those are resistive form of electrical or light generation. But when you have LEDs, these are electronic equipment, and there has to be power conversion from AC to DC for them to actually function. And by doing so, in some cases, they introduce harmonics. However, many of the harmonics distortion that they introduce can be negligible in most cases. Now, so as these higher frequency harmonics currents flow through the power system, they can cause communication error. Now, for example, for places where you have Internet of Things, where you have automation system, sometimes it affects the functionality of all of these automated systems because the kind of signals they get has been distorted. Some equipment, especially automation, where a system that has been automated, they use the footprint of the electrical system to operate. So once that footprint has been distorted, it creates confusion and creates distortion in the process. Sometimes it can cause overheating of the hardware, it can cause metering errors, and so forth and so forth. Now, these harmonic distortions can be they can be corrected and they can be cured using harmonic filters. Now, these are series of parallel resonant circuits designed to shunt or block those harmonic currents. Electrical engineers can clearly understand this. I mean, how you can actually prevent or correct harmonic. But for general knowledge, just know that to correct harmonic distortion, you actually use harmonic filters to do that. Now, another parameter we need to talk about is voltage imbalance. Voltage imbalance. So problems can occur because of voltage imbalance between three phases. Now, when we talk about voltage imbalance, we are talking about three-phase system. You cannot talk about voltage imbalance in a single-phase system. Voltage imbalance only is applicable for a three-phase system. Now, this can be a serious problem in motors, especially motors. It can be a very serious problem. Now, percentage voltage imbalance is found as a ratio of the largest phase-to-phase voltage difference from the average divided by the average. Now, I'm going to explain. We're going to even run some examples about how to calculate voltage imbalance. Because it's if you go to some facilities, you might find out that some lines or some cables are actually overheating, especially when you have three-phase connection, and you can notice that maybe either the red phase, the blue phase, or the yellow phase is overheating. Those are clear indications of voltage imbalance, and you need to actually check the load distribution across these phases, and then you have to balance it. How do you balance it? You just have to, move the load, some connections, move the load. If for example, there's excess load connected to one particular phase, you just have to move it to a less, loaded phase. So we're going to see how to do these basic calculations first of all. So for example, if we have 220, 215, and 210 volts in a three-phase system, now the average voltage, the first thing we do is to establish the average voltage across these three phases. So we have 220, we have 215, and we have 210. Once we check the average voltage, we can determine that the average voltage is 215. That's the average. Now we can now say, okay, how has this individual line, how have they deviated from this average voltage? So the voltage difference are 220 minus 215, which is 5. For the second phase, 215 minus 215, which is 0. And then for the third phase, 210 minus 215, which is minus 5. Now, the negative is not relevant here. Whether positive or negative, it is not relevant because they are, remember, these are an alternating current. So it is non-relevant. Now, what we need to do is that the voltage imbalance will now become the one with the highest deviation. And the highest deviation here is 5. Now, mind you, if we have minus 10, for example, this minus 5, assuming it is minus 10, then the highest deviation will be that minus 10. Like I said, the negative is irrelevant. It will be that 10. But in this case, we have 5, and we also have minus 5. So the highest here is 5. So we divide the 5 by the average, which is 215 volts, and they will have 0.023, okay, or 2.3%. Now, the voltage imbalance in this system is 2.3%. Okay. Now, 2.3%. Now, the question might be, at what level would it become a concern? At what level would it begin to affect the functionalities of equipment? Okay. So 2.3% is a bit is already So if it's above 1%, for me, if you're above 1%, it can begin to introduce some problems already. Okay, so for me, the idea is to keep it as, at plus or minus 1%. Now, this is another example just to help us, understand voltage imbalance. Now, this is essential and very, very critical for industrial applications, because when you go to industry, sometimes part of the problem that they will be having is voltage imbalance. And if you're not experienced or able to understand this knowledge, you might not be able to help them or solve the problem. So for this example, we have 400, 385, and 409 volts. Now, the voltage imbalance in this case is the maximum deviation from the average divided by the average voltage. And like we did in the other example, the maximum deviation here is 13. I think the maximum deviation here is 13. When you run this calculation, you realize that the maximum deviation is 13 and the average is 398. So when we do this calculation, we have 3.3% voltage imbalance. Now, there are so many. I've actually included some examples that we can play around with. This slide is going to be shared if it's not already shared with everyone. So just use this. You can run through these examples, some of these calculations on your own. If you have difficulty or if you have questions, please, I want to believe that all of us has been added to the WhatsApp group. Please reach out to Engineer Uche or myself on the WhatsApp group or on the personally on our WhatsApp number, and we can provide clarification and further further explanation. We may not be able to do all of that, in the course of this training because we are time limited. So what are the problems with voltage imbalance? So it can, when there is over voltage, remember, voltage imbalance can either be over voltage or under voltage. So if it's over voltage, it can cause electrical system overheating, electrical circuit failure, reduce equipment operating life, production and operation impact, and so many other things. Then you can have under voltage, lack of sufficient power to operate the electrical equipment. You have electrical circuit overheating as well, reduce motor torque, motor overheating, and so many other problems that can occur because of voltage imbalance. Now, let's talk about power factor. Power factor indicates how well the current and voltage are working together. A number of 0 to 1 is, so this is, it can also be 0 to 100%. So depending on how you want to talk about power factor. So in some places, it can be represented in percentage. In some places, it can be represented as a range between 0 and 1. However, power factor is more like it helps us understand the relationship between current and voltage. Remember, when we talk about electrical energy or electrical power, we define electrical power as a relationship, or more like when current and voltage work together to create electrical energy. That is electrical power, correct? Now, if current and voltage are not in perfect harmony, and I will explain what I mean by perfect harmony, then it can actually affect the power factor. Now, this is what I mean by perfect harmony. Now, this is voltage. The red wave is voltage, and the black one is current. Now, you will see that both of them actually, they reach their maximum amplitude. Now, maximum amplitude is the peak of their wave, of their frequency. Both of them reach their maximum amplitude at the same time. That is a perfect harmony, a perfect relationship between voltage and current. So once they hit their maximum amplitude at the same time, then there is no problem with power factor. Power factor is 0. Okay, it's not a problem. However, there's a problem when there's a displacement. If the voltage reaches the maximum amplitude first, then there's a problem. Or if the current reaches the maximum amplitude first, then there's a problem. And this is when you begin to have power factor issues. Now, power factor is equal to kilowatt. Now, this is an active power. Kilowatt is an active power. Why kVA is an apparent power. Now, kVA is the entire power that comes into your facility, but the actual power that you use to power your fridge, to power your light bulb, to do whatever you need to do is what we call the active power. Now, the difference between your active power and your apparent power is the power factor. Okay, so if your power factor is low, it means that you're paying. It actually means that there's a lot of wastages in your system. Now, there's an argument who pays for power factor issues. Is it the consumer or is it the power distribution company, or who pays for it? That's a discussion that we can have separately, but not here. So the ratio of how much of the power supply that can be used to perform useful work is what is what, of course, it is what we know as power factor. So power factor is independent of the type of load in the electrical system. It is independent of the type of load. Sorry, it is dependent on the type of load in the electrical system. What actually introduces power factor problem is the kind of load that you have in your system. That's what actually introduces the problem of power factor. So power factor reduces the amount of useful power. I think I've actually explained some of these things. And here, I've explained this diagram, what it means. But what kind of load actually gives you this kind of perfect harmony? The kind of load that gives this perfect harmony is what we call resistive load. And this is where we begin to talk about the different kinds of load in a power system. Okay? So we have resistive load. Now, resistive load, example of a resistive load is your, you remember those yellow bulbs, those yellow filament bulbs, those are resistive load. And because they waste a lot of energy, they are more of a heating element than lighting element. So they convert almost 95% of the electricity that comes to them into heat and just about 5% into light. That's why we've now moved, technology has now moved away from those yellow bulbs. Now we are now beginning to use LED, which are more efficient, you know, and even last longer. So this, so the LED, the yellow filament bulb is an example of a resistive load, but the one that we can easily relate with, which most of us use in our homes, are heaters, ions, electrical ions. These are resistive load. Now, 100% of the electricity that comes to them is converted to heat. 100% is converted to heat. Okay, so it can be assumed that they are 100% efficiency. They have a 100% efficiency, right? That's what it is. So in this case, there is no power factor issues. Voltage and current reaches their maximum amplitude at the same time, no problem. But again, there becomes a problem for inductive load. What is an inductive load? Inductive load are motors. We'll talk about motors. We'll talk about your fan. Your fan uses motor. We talk about your refrigerators. They use motor. Any mechanical movement that uses motor, induces is an inductive load essentially. When you go to industry, they have large motors, large induction motors. So this motors introduces power factor problems. Okay. So now what the problem here is that the voltage reaches the maximum amplitude first before the current. You can see that here. Now this is the voltage. Okay. So if the voltage reaches the maximum amplitude before the current, now kVAR are said to be lagging. Now kVAR is an inductive power. Is a reactive power. This kVAR is a reactive power. Remember, we talked about power. There's an active power, there's an apparent power, and there's a reactive power. Okay, these are the three forms of power. Now, power factor affects the third one, which is your reactive power. So when the voltage reaches this maximum amplitude first, there's a displacement. Okay, and in this case, you have an inductive load. So the motors. Example of inductive load includes the motors, transformers, and load with coils. All of these are examples of an inductive load. So the magnetic field in this equipment causes the current to slow down. That's the problem with some of this. And then you have a problem with power. So in this case, this power factor is usually less than 100. Your power factor is usually less than, that's an inductive load. Your power factor is less than 100. But there's another set of load, which is the capacitive load, which reverses the inductive system. Okay. Now, in capacitive load, your current reaches your maximum amplitude first before the voltage. Okay. And once this you have a capacitive circuit. So in this case, your power factor is more than 100. So this gives us an opportunity to actually correct the inductive lagging power factor, right? So, and that's why to correct a power factor, you actually need a capacitor bank to correct a power factor in a system. So we're going to see how you're able to calculate the amount of capacitor bank that is needed to correct any power factor in a system. So, but to help us understand clearly these different types of power and the power factor, we can use the beer analogy to actually explain this. So we have a glass of beer. The real thing here is the real power. This is a reactive power. And the reactive plus the real power is what you call the apparent power. That is the kVA. Ideally, what comes into your facility, what comes into your building is kVA. It's kVA. Now, depending on the kind of load you have, if you have an inductive machine, if you have an inductive load, you have motors in your facility, then you will most likely have this kind of system in your, where you have reactive power and you have real power. So the more you're able to reduce this reactive power, the better for the system. Now, there's a lot of calculation that goes in around this power factor and how to correct them. But again, we use a triangle to actually represent, the relationship between these three types of power. So the hypotenuse actually represents the apparent power, which is the actual power that comes into the facility. And then the adjacent, this is the adjacent here, which is the real power. We use this to represent the real power, and this is opposite. In our basic mathematics, we actually name this triangle adjacent, opposite, and then adjacent. We're going to see how to actually also use it in calculating these different powers maybe in the next slide. But just know that there is reactive power. So if you reduce this reactive power, so if you're able to bring this apparent power down to the red line, then you now realize that the reactive power is 0, and that is an inductive load. But the moment there's a displacement between the apparent power and the reactive and the real power, then you have a problem. So like I was saying, to help us do this calculation, now this is a turn-off for some of us because this is what we did in maybe universities and secondary schools, and we've not actually seen this being used in the real life. But in the energy system, yes, we have to do some of these calculations. If you need to conduct an energy audit, sometimes you might need to just use some of these calculations to actually do some basic. Now, these are basic anyway. It might not be basic to some people, but it's actually basic. If you understand the concept of SOHCAHTOA, this is what we learned in the school, in secondary school, actually. We learned the concept of SOHCAHTOA, and it helps us to understand the relationship between these triangles, okay? Remember, we've been able to represent these three types of power using a triangle. And to understand the relationship between them, we need to go back to the basic formula about this triangle, which is SOHCAHTOA, which is a Pythagoras theorem. Please ignore these scientific names, but SOHCAHTOA is an acronym that helps us to understand the relationship between these. So SOHCAHTOA means sine is equal to opposite over hypotenuse. Remember, I have defined this triangle, and I say that this is hypotenuse. The blue line is the hypotenuse, and it represents the apparent power. The red line is the opposite. Yeah, the red line is the adjacent, and it represents the real power. The green line is the opposite, and it represents the reactive power, okay? So if we are calculating for reactive power, we can actually come here and then see the relationship between this reactive power and what we know. Assuming we know the apparent power, and we know the cos pi. Now, the cos pi is the power factor. Now, this angle here is what we know as the power. This is power factor. This theta that you're seeing here is the power factor. It can be sin theta, it can be tan theta, it can be cos theta. Not actually theta, it's cos pi. We call it cos pi, okay, in this energy system. Cos pi means that is cos pi, PHI, cos pi, okay? So this is actually the power factor, okay? So now to be able to calculate any of this kind of power, we need to use this. I have introduced this just for simplicity. This is sine is equal to opposite over hypotenuse. Cos pi is equal to adjacent over hypotenuse. Tan pi is equal to, or tan theta rather, is equal to opposite over adjacent. Okay, so depending on what you need to calculate, right? Now, true power is equal to watts or kilowatts, okay? And then is equal to VA. Remember what we define power is voltage times current, right? Power is equal to, that's in terms of electrical system, is voltage times current times power factor. I remember I said that power factor is cos pi. That is power factor. in defining power factor, some people might not want to call it power factor, but once you hear or once you see cos pi, it means power factor, just so that we are aware of that. So this cos pi represents power factor. So if you do this multiplication, you can actually get, you can actually get the value of real power. Now, this is reactive power. Reactive power is the apparent power times sine theta. Okay, these are scientific nomenclatures. Sine theta is, and then when you expand this value, V is voltage, A is amperage, which is current, times sine theta, and you have the reactive power. And this is now these are right angle triangle rule. The square of the apparent power is equal to the square of the real power plus the square of the reactive power. This might not be used all the time, but it is good if you understand this relationship. Now, what we're trying to establish here is all the relationship between these triangles, so that in any case, if you understand this thing very well, you can be able to calculate any problem that has to do with power factor. I mean, the problem with power factor will not be a challenge to you. Once you're able to understand the relationship between this right angle triangle, then you don't have any problem with power factor issues or calculating power factor. Now, let's look at a simple example. If a true power is 700 watts and the cos pi is 45.6 degree, of course, if you use your calculator and press cos 45.6, what you're going to get is 0.7. Like I said, in this training, sometimes it might be essential to have your calculator handy so you can be able to demonstrate some of this thing on your own and then actually see them and be sure that what we are presenting here is the true process, and that you also follow and understand the process. If you press cos 45.6 on your calculator, what you're actually going to get is 0.7, and that is the apparent. So now the question is, what is the apparent power? Okay, that's the question. What is the apparent power? So true power is equals to, true power is what? Is equals to voltage times current times cos pi. And then, of course, if you do some rearrangement of this formula, so if you make VA subject of the formula, what that means that you're going to divide both sides by cos pi. So once you divide both sides by cos pi, you have watt over cos pi. Okay, and this cos pi, like I already said, is 0.7. Okay, when you do that calculation, so the true power, we have been given the true power to be 700 watts. So it's 700 watts divided by 0.7. And again, power factor is dimensionless. It does not have a unit. So that's why you're seeing that there is no unit there. Okay. So once you do this division, you're going to get 1000 VA. Okay. This is apparent power, and that's what we are being asked to calculate. What is the apparent power? In a further example, we are going to illustrate this with a diagram. But for now, let us also understand how power factor can be corrected before we go to further examples of how to calculate, apparent power, real power, and reactive power. I've already explained this before. This is a resistive load where voltage and current are in perfect harmony. There's no power factor issue here. But when you have an inductive load, then there's a displacement. To correct this displacement, you need a capacitor bank, which is a capacitive circuit to correct it. So when you combine this second chart with the first chart, you come back to the first to this perfect harmony, and that's why in power factor correction we use capacitor bank to correct power factor. So let us see how you can correct power factor. To correct power factor, that is we call this kVAR. There is a capacitor side that is needed to correct a power factor. We call it kVAR, KVAR. That is the reactive power. That's actually what kVAR is. How much of a reactive power do you need to correct a power factor? Okay. So it's a simple calculation. So the real power, in most cases, you will know what the real power is. So there's a table factor that you're going to multiply with the real power to actually know the size of the capacitor bank that you need to correct a real power factor. We're going to demonstrate that. Don't worry about this if you don't understand this from this formula. So the essential thing you need is the data that is needed is given. I mean, so essential data needed at a given load. the real power, the desired power factor, they use it. So this is just an example illustration of how this can be calculated. So let me show you what a table factor looks like. So this is what a table factor looks like. You can download this online. If you just check power factor table factor online, you see this table and you can be able to download it. So now this is a desired power factor, and this is the original power factor. So if you come to a facility and then you notice that they're having power factor issue, now you look at their original power factor, assuming that this power factor is 70, they have a power factor of 70 or 0.7, and you want to correct it to 90. All you need to do is to trace, this is 70, which is the original power factor. What is the desired power factor? The desired power factor is 90. You now trace this 90 and then see where it intercepts with 70. Okay, now this is 0.536. You multiply this value by the real power. Once you do this, you'll be able to get the kVAR. It's a simple and straightforward calculation. So let us illustrate with an example. Now, a facility is operating at a power factor of 70% with a real power load of 200 kilowatt. Now, this is the real power. How much corrective capacitance in kVAR is needed to improve the facility power factor to 90? This is just what I just illustrated. So in trying to solve this example, we come to the power factor table. Now, the original power factor is 0.7. We want it to be 0.9. We now look at the intersection between the desired power factor and the original power factor, and this is 0.536. Okay, we multiply this 0.536 with the original. We multiply with 2000, which is the real power, right? So that's what we'll do here. So the real power is 2000. The table factor is 0.36, right? So once we do this multiplication, we'll get 1072 kVAR. So this is the capacitive or capacitor size that you need to correct that power factor from 70 to 90. So the answer is D, 1200. Now, some of these examples that you're seeing here are actually pulled out from test questions. Or so for some of us here that are desiring to become a certified energy auditor or a certified energy manager, which is what this program is also going to help you to do. Most of what we're presenting here are the same thing that you're going to see when you go into some of this training. If you want to become a certified energy auditor, a certified energy manager, you need to understand what we're talking about here today. Okay, so this example that you are seeing was pulled out from the question banks of these exams. I myself am a certified energy auditor, I'm a certified energy manager. I've gone through this process. Engineer Uche has gone through this process as well. So we'll talk about this and we are saying this and we're presenting this from experience. So essentially, this is the before. You have a power factor of 70, and this is after. By the time you reduce this power factor, you actually reduce it, to 90, and this is what you actually have. Your kVAR would have reduced from, from what it was, to the new value, whereby your now power factor is 90. Okay. So this is a test question. A facility has a 100 kilowatt electric resistant oven for drying parts. What is the power factor of the oven? Please, this is a question. Is a test question. You can unmute your mic and ask. And answer. 100. Okay. Does anybody disagree with this? Is anyone in disagreement with the 100% answer?
No, we concord.
Okay. Because it's a pure resistive load. For every pure resistive load, the power factor is 100. Now, this is a test question. A facility has a motor that draws 200 this is apparent power. kVA is an apparent power and has a power factor of 70.7%. How many kilo? Now, the question is asking for the real power. How many kilowatt and how many kVAR does it draw? Because of time, we may not be able to, explain, but I have provided the solution to this this question. You can go through this on your own. If you have questions, if you don't understand this, I'll always be available to respond. But there's something I want to illustrate here. Something I just want to explain. Now, the power factor is So it's given in percentage 70, right? And remember I told you that the power factor is cos pi. Now, cos pi here is 70. Now, but you need to determine what the angle is. Now, this is the power factor. You need to determine what the angle here is, right? So what I'm explaining is that when you're calculating your power factor, you don't go and do sine 70 or sine or tan 7. No, you don't do that. You have to first of all determine what the angle here is. So you use your calculator to do. If you use your calculator, you have to do what we call cos inverse. If you do if you do a cos inverse of 0.7, you have 45 degrees. So this angle here, this angle that you're seeing here is 45 degrees. So you now apply this, whether you want to use sine. So for example, in this solution, you can see that we have used sine here. Remember, power factor is cos theta or cos pi. But again, you need to know what the theta is or the pi is. And that's what we'll try to do here. You have to first of all establish that angle, right? Should in case you need to do sine 45 or tan 45. But that's more like trying to give you a kind of a leeway in trying to understand what we have done here. But it's self-explanatory. If you go through this solution, you understand it. If you don't understand it, please come back to me. This is a test question 3. I have some of these test questions just to help you. I need to move faster because we have our time is fast spent. So I need to talk about power computation formulas. Now, when I talk about power system, we'll talk about different phases. We have single phase, we have 3-phase. There are different formulas to do this computation or to calculate single phase system and 3-phase system, but the difference is not much. So for a single phase system, it is voltage times current times power factor. It's as straightforward as it is, okay? That is for a single phase system. To calculate the power is voltage times current times power factor. Now, for a 3-phase system, is a slightly, we introduce the root 3. Now, remember that 3-phase system has 4 wires. One is neutral. They have the yellow phase, the blue phase, and the red phase. These 3 phases. Now, you need to introduce root 3 to be able to calculate the power across these 3 phases. Okay, and that's the only difference between a single phase and a 3-phase. So whenever you see, whenever you're solving any problem, whether in real world or in exam situations, you need to consider if it's a single phase or a 3-phase, and you apply the appropriate formula. Root 3 is also the same thing as 1.732. So if you do this root 3 in your calculator, you're going to get 1.732. So in some cases, you just apply 1.732 straight to make the calculation easier for you. So this is an example. Like I said, this is a straightforward example. The formula is straightforward. You just need to, extract your values and input into the formulas, and you run a simple calculation. This says calculate the power consumption of a 10 ampere 120 volt AC single phase electric resistance space heater. Okay. Now you just extract you'll be given your current, you'll be given your voltage, and your power factor for a resistive load is resistive load is just 100 or 1. So it's just a straightforward calculation. This is an example too. This is for 3-phase system. Okay. And there's something I just want to conclude with, which is electrical demand load factor. When I was talking about electricity, pricing of electricity, I talk about demand charge in some cases. It's not applicable in Nigeria, but when you move around the world, you begin to see. So in fact, Nigeria has the simplest electricity tariff structure, the simplest electricity. And I'm saying this from experience. In the course of my work in doing consultancy, for project development, I've worked for projects in Kenya, Cameroon, and I can tell you for free that Nigeria has the simplest electricity tariff, because in our project development, we need to do both technical and economic assessment of this project, right? And you need to take into account of the electricity tariff structure of the existing economy of the existing system. So when I get this document of the electricity structure, sometimes I need days to study and understand their electricity structure and their tariff system. And when I compare that to what we have in Nigeria, our own is the simplest, because we just have a straightforward kilowatt hour charge. In some places, you're going to have so many different, you have demand charge, you have, what did they call it again? I mean, so many charges. You have, okay, depending on the price of fuel. I mean, there are so many things that moves anyway. But let's not go into all of that. But the point I'm trying to make here is that in some places you may have the you know the uh you may be faced with a challenge where you need to calculate demand charges or demand consumption or demand capacities of a facility. And this is important. If you're sizing a generator, you need to also pay attention to to the demand of the facility. Now, let me give us a typical illustration of why this is important. If you want to size a generator for a facility and their energy demand is, for example, 100 kilowatt. Now, I'm sorry, not energy demand, their power demand is 100 kilowatt. 100 kilowatt. I need to conduct I mean, this is what you actually concluded after you've done your survey, or what the facility manager has told you, that our demand here is 100 kilowatt. But as an energy professional, you want to help them, make the best economic decision, right? And you cannot begin to ask, okay, what is actually driving your 100 kilowatt? If you look at their energy profile, for example, if they're able to provide the energy profile, you can see what is driving that peak. So it is possible that they are running two heavy equipment at the same time. Maybe during the day, they are running, so if this is an industrial facility, okay, let me use the domestic facility, maybe a residential facility. During the daytime, they are running their washing machine and they are running their water heater at the same time. Okay. Now, when you run these two equipment at the same time, you shoot your demand. It goes up. But as an energy management strategy, you can say, okay, no, you need to introduce an energy management practice. Please don't run these two equipment at the same time. If you need to run the washing machine, please don't run the water heater. If you're running the water heater, don't run the washing machine. Now, what this helps you to do is that you're going to actually reduce the size of generator that is required to power this facility, right? You're going to reduce the size, and you're also going to improve the efficiency of that generator. So let me give a typical example. If you go into a facility and you see a peak demand in that facility, and that peak demand is, for example, 80 kilowatts, and this demand happens only once in a month. So, for example, okay, let me say once in a month. Okay, maybe it's an equipment that they use only once in a month has introduced this peak demand. When you're sizing your generator, you must size your generator to meet that demand. In as much as it only occurs once in a month, but your generator has to meet that demand. What happened actually is that for every other time of the month, that generator is performing, is not optimized, it's performing below average, unless that peak demand load comes on. Now, if you see that kind of situation, you can then advise, anytime you need to use this equipment, please shut down every other equipment so you don't need to create unnecessary demand. Now, these are energy management strategies, how to actually reduce your demand. Now, but for us to understand this, and that's why I have put this electrical demand load factor here, just for us to understand how demand factor affects, our energy bills and sizing of our equipment. Okay. So when we have, for example, now this illustration is for grid connected. I've spoken a lot about generator, yes, but this illustration is for grid connected, and this is presented in a scenario where you are being charged demand cost. I mean, where you pay for demand charge. Okay, so if you pay for demand charge for example, if you're living in America and you have a demand charge component in your electricity tariff, how do you calculate that, and how are you able to manage that? Now, your demand, your load factor, which actually is what translates into your demand, is the actual kilowatt hour. Now, this is energy, actual kilowatt hour use divided by your peak times time. Divided by your peak times time. Okay, so this is how you calculate your load factor. So assuming you have a generator, now this is for grid connected. Okay, but let me bring it in the context of a generator. If you have a generator that is maybe 100 kilowatt, 100 kilowatts essentially might be like 120 kVA, right? But let's say 100 kilowatt. And you put a load of let me say you put a load of 80 kilowatt on that generator. For every time that generator is working, you have a load of 80 kilowatt. Then what that means that the load factor on that generator is actually 80%. Okay, it's actually 80%. I'm just using this illustration to make it simple, using 180 and assuming that that load remains 80 constantly. But if that load is, for example, the generator has a capacity to produce 100 kilowatt. If you're using 30 kilowatt, for example, then what that means that the load factor of that generator is 30%. I'm just using this to sorry. I'm just using this illustration just to make the explanation simple, okay? So now, if you imagine this diagram that I have here, now this is the green area is your peak demand. And this peak demand, for example, maybe when you on your heater, then you hit this peak demand, but every other day, this is the actual load. Okay. Now, what this means that your peak your actual energy consumption, let me see. So if you imagine that the energy used in the use of a building over the period of 1 month, the load factor will be the blue area. That is this blue area divided by the sum of the blue and the green area. So I just use this to do a simple. So the green area is actually represent your peak, right? Your peak demand, which is what you have here, your peak demand, okay? But then your actual energy consumption is your blue area, which is this, what you're dividing with, or what your numerator actually is your actual energy consumption. Then your denominator is your peak demand times the time that you use this power. Okay, that's what I'm trying to explain here. So once you do this, you'll be able to clearly establish what your load factor is. Now, a high load factor means that the building has, when I say a high load factor, so I'm assuming that the first illustration I gave you where a facility has 100 kilowatts and then you're using 80 kilowatt, that's a high load factor. That is a good one. Okay. What that means that you're actually the system is actually optimized. But if you have 100 kilowatts and you're actually using 30 kilowatt, it's not good. And let me just also add that for diesel generators, the minimum load factor that you can put on a diesel generator to still allow that generator to work well is 30%. Once you go below 30% on a diesel generator, then it becomes harmful to that generator. It creates problems for that generator. And when we're going to talk about solar system, we're going to talk about this as well, because for solar designs, in some cases, you have to integrate the generator into the solar system. Once you integrate generator in a solar system, and because of excess energy production from the solar system, you begin to reduce the demand from the generator. Once the demand from that generator reaches 30%, what is going to happen at that point that you can no longer reduce the demand from that generator below 30%. What is going to happen at that time? You begin to curtail your solar system. So your solar system will be curtailed instead of generator. So this is why it's important to understand this load factor and demand, and how to balance them in your design system. I think I've explained this already in terms of your demand strategies to reduce your demand, your load factor, or to increase your load factor and actually reduce your demand charges if you're paying for demand charge anyway. So these are ways. So some of them are more like load shifting, where you have to shift your load from a peak period to a non-peak period. Okay, you just have to move your load. You understand the energy consumption of the facility, and then advise on when and when not to consume those energy. So this is a typical example of peak demand or a load factor. So compute the monthly load factor when peak demand is 1,250 kilowatts and energy use is 500,000 kilowatt hour. The time in that period is 720 hours. So that is about 24 hours per day times 30 days per month. That gives 720, sorry. So when you want to compute the load factor, it becomes the actual energy consumption, which is 500,000 kilowatts, divided by the peak demand, which is 1,200, 200 kilowatt times the hour, which is 720. Once you do that, you get 55.6%. 55.6% is not bad, but in our design processes, let us please aim at 70%. In our design system, when you're sizing generators for facilities, try to see how you can maintain a load factor of 70%. And how can you do that? Please understand their consumption pattern. It's very important. Something like this. You need to see their consumption pattern and then ask questions. You need to ask what is driving that peak. Is it possible to move those consumption towards off-peak period so they can be able to optimize and then at least have a higher, a higher load factor? This is very, very important, especially when sizing a supply system. When I mean a supply system, you're designing your solar system, you're recommending a generator size or anything that supplies electricity. You need to have this good understanding of how this energy is going to be consumed, and then you can be able to advise, appropriately. So thank you very much for staying true for today's training. I'm sorry if I have rushed through some of the slides. Like I said, I'm sure if Engineering hasn't shared it with you, he will share it with you. And if you go through it during your own personal time and you have questions, please come back to us. I will be able to address them. Thank you very much for staying true, and thank you for your active participation and active listening. I don't know if there is question, comment, suggestion. How do you think we can improve this program going forward?
Yes.
Thank you.
Yeah, thank you, Engineer Chima. That was a beautiful one. And just like we always said before our training, we are all here to learn from each other. Okay. I think one of the challenges we're having today in Nigerian engineering sector is our ability to, form that nexus between the academic and the industrial experience and the business sector. So I think all of us were here to learn, both the resource persons and the participants. So in the next 10 minutes, I would like to hear from us. Let's get your feedback. This is day 1 of 8 days, 8 days, 8 weekends. So let us see what some of us have to say. The program is 10 every Saturday to 12 o'clock. I have shared these materials, and in the email, register on time so that you can have those materials on time. And I think I've done justice to that. I sent this material earlier on so that we can go through them and kind of get familiarize ourselves with them. So having said that, do we have questions both for the content of what Chima have introduced us to today, or to the arrangement we have on ground, or if there's any peculiar kind of a perspective from any of the participants? I think we would like to give you at least 1 minute to share with us. Thank you.
Thank you, Engineer Shima. That was highly impactful. Please, I have 3 questions. Can I go ahead, sir?
Go ahead, please.
Yes. I have one on global warming and I have 2 on diesel generators. Yes, at the beginning of this lecture, you mentioned that the Western world, America and Europe, that they contribute more to global warming, while African countries suffer the climate change the more. So I'd like to know why it is so. Then, apart from that, I have 2 questions on diesel generator. My first question is on a voltage imbalance. If you have 3 phases on a generator and the voltage of one phase is 200, the other one is 215, and maybe the third one is 250 kVA. So how can can voltage imbalance affect the functionality of a diesel generator? And my last question, sir, the second question on this generator, you said if the load on a generator is less than 30%, that it is not okay. Maybe for a 100 kVA generator, you are running it at 25 kVA, that it is not good to do so. Please, I would like to know why. Thank you, sir.
Okay, thank you very much for your questions. For the one of climate change, it's a global phenomenon, and for the fact that, like I said, it's more like in as much as the world is too large, it's still like a shared community. So what somebody is doing at one end, affects, what's happening at the other end. So remember that we're all connected through the same source of energy, which is the sun. Remember, the same sun that comes out, that produces the sunlight, shines in America, shines in Africa, shines everywhere. Okay, so it radiates across the globe. So whatever is happening at one part of the globe has impact on other side of the globe. So if, for example, there's an excessive heat for example, there's an excessive heat in, say, in America, okay, and it has causes maybe, for example, drought. And I wanted to think about that. Now, when there is a drought in a particular region, meaning that there is no rainfall in that region, correct? Now, what actually happened, because of the temperature differential, the rain that is supposed to come down in those regions has moved to another region, okay? And you don't know where that would have moved to. So, and that's why, so for example, it may have moved because of excessive temperature in a particular region, it may have moved to, so for example, it may have moved to Africa. And then what happens is that when the rain wants to come down in Africa, it will come down more than the required quantity that it should have come down in Africa, and then it causes flooding, right? So it's a shared community, and this is how it affects, the entire world, whether in America, in Europe, or in Africa, right? However, the consequences are more in some certain regions because depending on their climatic condition and their topography, right? Maybe the way the nation has been structured, and that's why people keep emphasizing on the plantation of trees, right? If you plant trees, these are ways to mitigate climate change, plantation of trees, to actually absorb the carbon dioxide that actually comes out from the burning of this fossil fuel, right? So depending on the climatic condition of some certain regions, it actually helps to manage this global crisis. So that is how, this is being affected across the world, I mean, irrespective of where you are. And then the one of generator, you asked about the voltage imbalance, if it affects the functionality of the generator. The effect is felt more on the consumption side, on the cables. Remember, we have wires that connected from this generator to the equipment where you need to power those kind of load. I have excess energy in one of the or excess consumption, excess power connected to one of the phases. It can actually lead to fire outbreak because there is going to be high demand on that phase, whereas the other phases might not be loaded as much as they should. So it has more impact on the wires and on the load. If you're connected to a three-phase load, then it has impact on that load, more on that load. It has impact on the generator, on the on the functionality of that generator, but it's more on the cables and on the load. Then the other question you asked about the loading a generator below 30%. Yes, when you have a generator loaded below 30%, it creates a lot of problems. One of the problems that you can also create is incomplete combustion of the fuel. You have diesel that's input. So we'll go to, by the time we get to some industrial, we'll talk about combustion, you begin to understand how this also impacts, combustion, because essentially what's happening in a generator is combustion. Only that in this case is a compression for diesel generator anyway, it's a compression cycle, not for petrol. Petrol is an ignition, but for diesel is a compression cycle because, so it affects the combustion of those diesel. You might have an incomplete combustion. And what that means that you burn more diesel, to generate less electricity than is required. And it also affects, because of incomplete combustion, you begin to build some soot and some in the generator, and it leads to
carbon.
Exactly, it leads
carbon
to
monoxide.
Yeah, when you have an incomplete combustion, you have carbon monoxide actually. But beyond that, there are some other, things that
carbon deposits too.
Exactly, forms in. So you need to more frequent servicing of that generator, and it can lead to, so it creates a lot of problem for the generator. So that's how it affects the generator. I don't know if that clearly answers your question.
Yes, thank you, sir.
Yeah, that's a good one. Chuks Agwala. Please
Okay,
make it brief.
well, just on the issue of climate change, I think the major challenge is the fact that most of the Western countries also have, due to industrialization, they have also sort of gained a very high, like an unassailable, or let me just say an advantage, even in financial terms. So in terms of disaster recovery, they have higher resilience. So most African countries will not have as much, both whether technological or financial means, to be able to recover from disasters as much as they would. So that is why the effect is felt even much more in like third world countries, whereas they are not the main contributors to issues that have to do with global warming or climate change. So that was
All right.
just a
Thank you.
perspective I wanted to offer. Yeah.
Okay, that's a good one. Thank you. Thank you for that perspective. Please, any other question? Some people joined us late. Please, this training is 10 a.m. to 12. We are kind of overshooting today because we started a bit late, being the first day. But please, I want to encourage us and I want to grab our indulgence. Let our 10 o'clock be 10 o'clock. And our 12 o'clock be 12 o'clock. We did some introduction today. Subsequently, we just moved to the class. Like I said, Chima, can you stop the recording, please, from your end? Okay, I stop it.